continue. Yes. Okay, thank you very much for this kind introduction. And thanks to the organizers for having me here as one of the invited speakers on this topic, stratified binary layers and turbulence, which is, happens to be one of the topics I've been became interested in over the years quite well. But not the only topic actually I've been working on. In the last 45 years, I realized that it's now my 45 years anniversary in this field of turbulence when I started in 1977 as a relatively young scientist working with Frans Nieuwstadt and Han van Dop, Henk de Bruin and other great people at KNMI. And actually I learned much of this field, not because of my background, good education perhaps, but mostly by working with them and learning by doing. And this is an advice I would can give to all of you, particularly young people. Find a good tutor who's active in the field and interacting with him or her, and then start analyzing data. And I was lucky to start analyzing data from the Cabot Tower, which was just in that time producing the first profile data and turbulence data. And and I will touch a bit upon that. I like very much this 100-year overview of turbulence, but I will focus mostly on some achievements of the last 50 years, particularly, and those topics are covered in the balloons. I will talk about how, of course, at recognizing Innsbruck as being a great place to visit, but also talk about how the Prandtl number depends on the Richardson number. There has been quite issues on that in the literature. This is one of the graphs in which I have shown here in blue. Then about stable binary layers over ice, but also over generally level terrain. And I had to summarize and revisit some of the issues of the GWX atmospheric binary layer study cables, which I happen to co-chair with Gunnar Svensson from Stockholm University. And then, of course, I comment on the great painting by Vincent van Gogh at the end. Okay, stable binary layers. It's a nice cartoon by John Wingard from '85. Summarizes quite nicely what is the main issues. That's small-scale turbulence, but also breaking waves and interactions with the lower level yet at the top of the stable binary layer, typically at a height of 200 meters, but can be larger or even smaller. And shear production of turbulence gives then rise to momentum exchange and also turbulent exchange of fluxes towards the surface. Now, this is a long history of research in this field on turbulence and heat flux and momentum flux formulations, and also about the depth of the binary layer. And that starts actually, in this case, I would like to focus to the work by Sergej Stilitikevich in '72, by Brost and Wingard in '78, and by Frans Nieuwstadt in '84. But there have been many others active in this field as well. When I started at KNMI, one of the first papers which Frans Nieuwstadt gave me to read was this paper by Stilitikevich, which is a very short paper. I think it's only about 7 or 8 pages. He published it in '72 and has no observations. It has only theory and some scaling arguments, but very nice scaling arguments where he showed that the boundary layer depth for a turbulent boundary layer, stable boundary layer, is connected to the friction velocity over the Coriolis parameter and the Obukhov length to the square root. And of course, for mid-latitude boundary layer. So it would not apply for the tropics because the Coriolis parameter would be 0. And typically it's also not valid for neutral cases because the Obukhov length becomes infinite. So I would say practical H over L, the depth divided by the Obukhov length should be larger than 1. Then you have a good approximation. And you can, of course, take care of those limits very well. And Sergej with his co-workers did this over the years and came with, in fact, with many proposals which have been if you look into these papers, every paper has different coefficients for in front of this equation. So there is some uncertainty in this coefficient C. And it mostly relates, of course, to other aspects because there are many issues in the real atmosphere which are also important, like, for instance, the effect of upper level stratification given by the Bruns-Vaselaar frequency, which is not covered in this formula. But you can take care of that if you and combine this. And of course, this is also related to flat terrain. With the typical type Dutch binary layers, this type of formula can be is recognized and can be seen, disapproved, but in many other cases not, because other factors play a role as well. Now, but important to note is that the format of this equation is confirmed by many other studies and also by experimental work, but also theoretical work, like the second order modeling from Roast and Wingard of 78, which is actually a very nice paper to also to revisit if you are new to this field. They actually were one among the first where they took the full budget equations, the second order closure equations of, in this case, for the stable bound layer, with some suitable, reasonable approximations for the difficult terms we normally neglect or make very simple approximations for. And they came up with quite interesting results that for stationary boundary layers, that the diffusivity for momentum in particular behaves very well like a profile function, this diffusivity, depending on the stability from left to right. Left is less stable, right hand side is more stable. And this comes out apparently by solving the full set of second order model equations. Then of course you can realize why would you solve then all the full set of equations if this comes up all the time. And this notion was picked up later on by, for instance, by Itron and Larry Hart in a paper by 78, which became a very classic paper, where they said, okay, we use these profile functions for momentum, for the diffusivity of momentum, and a similar one for heat, to make for practical applications. And this became very popular in the WRF model and in the MM5 model, and I myself applied it in the NCAR climate model, and it ran very well and great with high computational efficiency without solving the full equations. You got pretty good results. But you had to diagnose, of course, the depth of the boundary layer. And that is, you need some insights and physical insights how the boundary layer work to do this a proper diagnosis. And many papers on that issue appeared as well, including work by myself, but I have no time to go into that detail at the moment. Rather, I would like to emphasize that Roos and Wingard also confirmed the formulation which Sergei Sinterich put forward intuitively on scaling arguments. They more or less confirmed that format as well. Now, what Frans Nieuwstad did in '84 and published in '84 in the Journal of Atmospheric Sciences was actually simplifying the second order moment equations from a different perspective with some other approximations for the unknown terms. And by doing so, he actually came up with a simplified set of equations, which ultimately led to the local scaling approach, which was already mentioned this morning. And he compared the outcome of his simplified model, which is here in the full lines, compared it with the Cabot data over a big set of Cabot data classified in terms of Z over lambda, and lambda is the so-called local book of length. It's the same form as the book of length, surface book of length, but in this case you use the local observed fluxes for momentum and heat. And then it organizes quite well for the Richardson, for instance, on how the Richardson number depends on stability at the left-hand side. And also for the momentum, for the eddy diffusivity for momentum, the upper graph, or the heat, the eddy diffusivity for heat in the lower graph. But as you can see, there is some mismatch between the data and the solution of the model. And this is particularly for the near between, let's say, moderate stability conditions. For the large instability, it works pretty well, but for the moderate conditions, it does not work that well. And that is related to the uncertainty of the gradient functions for momentum and heat, even in terms of local scaling. So referring to the monovocal similarity functions. So this means that the Cabal observations do not really confirm the, at least according to this data, the gradient functions for heat and momentum in this particular case. What I would like to point out is that also that Neustadt selected cases for sufficiently strong winds, which means that stable, really stable cases were not considered. So basically the Richardson number is smaller than 0.3 or so. So it's a limited set of data and analysis, but still it appeared later on that these local scaling ideas are still useful also describing more stable turbulence. And then stepping further to second order model equations, Silitinkiewicz and others listed here refined this or extended this also with the so-called hierarchy of energy and flux budget methods, which gives a nice overview of the second order equations with all their extensions which we have in the literature, including the many simplifications. And by doing so, they came up with this result for how the Prandtl number depends on the Richardson number. Now, typically for Richardson numbers, the neutral till, let's say 0.2 or 0.3, the Prandtl number is around 1. It means that the differentiabilities for momentum and heat are similar magnitude. But if it becomes more stable, the Prandtl number increases with the Richardson number. And in the closure of Silitinkiewicz and co-workers on this particular paper, this behavior at the stable side, very stable side, is related on how the potential turbulent energy is related to the kinetic potential energy, kinetic energy. And that ratio defines then the slope of this curve. But he did not show an analytic solution for that, but he did compare their results with particularly laboratory data, as is indicated in the figure. But some uncertainties exist. And I was very much inspired actually by this paper. And I studied on this quite, spent a lot of time. It's quite compact, it's a lot of equations. It's great to sharpen your brains, but you need to revisit many times before you get a glimpse, I think, for what you are really trying to do. And we tried to, and by doing so, I started working with Sulkanta Basov, which is now at Delft University of Technology in the Netherlands. And we were able to refine this and come up with an analytic solution how the Prandtl number is depending on the Richardson number. Depending, of course, always on a couple of coefficients which are uncertain, which do have a physical meaning. Like this C5 coefficient is actually the Prandtl number at neutral conditions. And this AP is, for instance, related to the counter gradient term in the heat flux budget equation. It's the buoyancy correction on the pressure temperature correlation. For the persons who are involved in this, you know what I'm talking about. For those who heard this for the first time, it's a mess. So you have to visit the paper. But what's interesting is that we could derive this analytic equation, and as such also represent many of the earlier findings in the literature. And we call this the LSR approach because it refers to how you deal with the length scales in stable turbulence. There are many length scales have been proposed over the years, and yeah, they are all connected, and it appears that if you treat them well, then you can come up with this equation. There have been in the literature, and the next speaker may talk about this. If you plot in this way, there might be spurious correlation or self-correlation. But we are so confident about this theoretical result which come directly from the budget equations that we still decided to plot it like this. And in fact, we can represent by playing a bit with the coefficients, with the uncertain parameters, we can represent the previous proposals in the literature, empirical approaches in the literature, or some alternative theoretical approaches like the one by Zilitikevich et al. And also by Gabi-Katul et al., which come up from a different spectral approach and all going to the same type of results, although it's on logarithmic scale, so you notice this, so there is a band of uncertainty there as well. What was interesting to see that Thomas Vogel recently used this argument that the Prandtl number should be larger than 1 for the very stable cases to explain some of the counter-gradient fluxes in his data. And Thomas knows much more about this than I, so if you have any question on this, we will pose it to him. I found it interesting to note that this is also really relevant to explaining the behavior of decoupling at the surface in very stable boundary layers. Then, yeah, you know, and Pensionado, emeritus professor, losing lack of skills of computing, has to think about and going back to the analytic approaches. And we decided to look at the boundary, Ekman boundary equations. Now, this is a classic solution for the set of equations for both the northern and southern hemisphere. So that's why we included the sign of the Coriolis parameter as well as the magnitude and distinguish between that. And typically you can solve this for a constant diffusivity, then you have the Ekman solution. Or you can do it for profile functions of diffusivity like Franz Nieuwstra did and others did. But rather than assuming a value for the diffusivity, we discovered came across by playing with the equations that why not make an assumption for the momentum flux profile? How the momentum flux varies with height. Just very simple, like is depicted here in the middle of the page. The friction velocity locally squared, the momentum flux, is related to the surface flux times 1 minus c over h, a profile function where to fact power alpha, which is unknown. But typically in the literature you find alpha to be 1.5 or 2 for neutral boundary layers and for stable boundary layers. And by doing so, and I have no time, this paper is accepted now for publication in a special issue of dedicated to the memory of Sergei Zilitikevich. It is also available in the archive, so you can find it. But in fact, by assuming a momentum flux profile, we find that the diffusivity, which comes out of that, is consistent to what Prost and Wingard already had with a second order closure model for the very stable case. And what local scaling also provides. So connecting the various theories with each other. And also the Zilitikevich height, again, for that particular limit. So it's nicely how these various angle of attack, theoretically modeling observations are converging. So this is actually nice progress in our field, I would say. As many of you might know or know, is that I have been in the last 25 years, or 20 years, I've been active as a co-chair of the GWAT Atmospheric Turbulence study, which is part of the World Climate Research Program. I started in early 2001 or 2002, realizing that there are many models used in practice for weather forecast and climate models, which have been quite different. And we noticed that particularly about modeling for these stable boundary layers it has been difficult and was still a challenge. And with many sensitivities to details in the turbulence mixing formulations. So we came up with a strategy to enhance our understanding and also our understanding, but also our modeling capabilities by organizing benchmark studies. Starting from relatively simple case over ice, inspired by observations, but by setup of large edge simulation by Branco, and in fact by one of the co-workers. And then came on from left to right, adding more and more complexity and interaction with the surface and with other processes from Gables 1 to Gables 4. Gables 1 was of the particular case in the Arctic, and Gables 4 ended with the Antarctics, and Gables 2 was for the Midwest of the United States, and Gables 3 was the intercomparison for the Dutch Tower of Cabau. And I will show some results, and I think many of you know them. It is that models at that time, in the early 2000s, showed much too strong mixing in stable conditions. And that maybe is triggered by what was formulated by European Central Weather Forecast model, because they use enhanced mixing formulations to compensate for other factors in the model which did not work well, like the lack of gravity wave drag and all of that. And some models still do this. And typically operational models at that time had a factor of 2 deeper binary layer than what you actually can motivate on basis of large edge simulations or observations. And that directly also impacts on the turning of wind with height, as you can see at the right-hand plot. And where the green is the reference case on basis of a large edge simulation model for the simple case. And the other curves are by operational models, the blue ones are by research models. And you can find of that in the literature. And I think this helped quite a bit of the understanding and triggered many people to look in their specific model and make a comparison of their model with this benchmark. Now for Gables 3, we also did large edge simulations in comparison with observations along the Cabau Tower for this particular case for a period of 6 hours, and this is the end results. And overall, the models behaved quite well in comparison for the mean data because the forcing was good, but also in comparison with the fluxes. And where the solid line is the median value, and the gray zones give, of course, the uncertainty in the variety of model results by the different LES models which took part in this intercomparison. Recently, this was also done for the Gables 4 period, for a very stable case in the Antarctic with a very shallow binary layer of only 20 meters. And then you do notice that different models which are in use do produce, even large eddy simulations with the highest resolution do produce different depths of the binary layer. And this is related to their subgrid closures, basically, given the state of the art. And Fleur Prouvour has nicely summarized these results in a recent paper, also in binary layer metrology. And also realized that the models were producing quite different values for the stability, H over L, typically between 2 and 4. Here in this, this scaling diagram, which is from the 80s, so it's not involving the isotropy issues yet, but this one is summarizing how we at that time believed that the various scaling regions in the binary layer would connect to each other, from surface layer to the local scaling region to the Z-level scaling region, shows that how in the various Gables runs, the stability has in fact increased from Gables 1 to Gables 3 and even to Gables 4. Also indicating that we, with our current capabilities, are able to do quite a good job for more stable cases using LES models in particular. But then if you go back to Gables 3, we also ran operational models, weather forecast models, and climate models at that time, all with the same initial profiles and forcings for the atmosphere, but with their own recipe for doing radiation calculation and surface budget treatment, surface flux treatment, although with all with the same prescribed albedo during daytime. And then you can find a quite large range of results. And for the outcome, the black dots are the observations which should be represented, and the colored lines are the various model outcomes. And it appears that this is not so much depending on what the various models have been using for their turbulence scheme, but in particular the interaction with the surface. And that also impacts on the result, for instance, for the strength of the low level jet, which is quite sharp here, as indicated in the black dots in this figure as well. So the sensitivity to the interaction with the land surface. So it's not only about turbulence, it's also on how turbulence interacts with other small-scale processes in the atmosphere. This is maybe lessons which we learned from the scale study in particular. Now, recently we became involved as one of the co-workers in this ISOBAR innovative strategies for observations in the Arctic atmospheric binary project, as directed by Joachim Reuter, and I understood that we will talk about this later on, so I will not spend too many words on this. It's quite a complex case to make observations of a stable binary layer for such a region in the Nordic hemisphere. But if you then use a model trying to state-of-the-art model, in this case the weather forecast model, WRF model, then it's not actually not doing too bad for its turbulence parameterization, if as long as you prescribe it with the knowledge, suitable knowledge of the surface information, particularly the ice properties in this case. For the 3D, the full three-dimensional models had difficulty with this, representing this, but a single color model was actually quite capable of picking this up. And this is just recently published in this paper, which I quote here. Now, that brings me to another aspect, is that although we review here 100 years of turbulence, but it's obvious that this turbulence is, you cannot study this. You can study this, of course, in isolation, and we have learned quite a bit of turbulence by studying this in isolation. But for the real atmosphere, and you're talking about meteorology and weather and climate, we have to be aware of many other aspects, small-scale processes, which we have to deal with, and which do interact with the turbulence as well. And Red-Jan summarized this quite nicely in this diagram. And it's clear that the world is not flat. I borrowed that title from a paper of Matthias, so it's clear. Although it's also clear for a Dutch person that the world is not flat. And another aspect, of course, for very stable boundaries is that it impacts enormously on health. And it still does in many cases in the world. We should not forget about that. Cases in the atmosphere with small winds or really almost no wind produce these fog episodes, and of course pollution, which is not spread. I think that covers what I think has happened, say, in the last 100 years, but with the focus on the last 50 years. And I think that over the years, you can say safely that the theory and insights have evolved, and as also demonstrated here in this morning. But certainly in the first 50 years over time, evolved slowly. But also I must say that many of those important insights of the, let's say, of the first 50 years have been forgotten afterwards. And like this Rosby and Montgomery paper like we showed this morning, it's very interesting to revisit this again, and that's what on my do list to revisit this paper and see what we can learn from that. It's also clear that enormous enhancement has been in understanding of binary layers. I think that's often, and that is because we can do this. Field have been doing this field campaigns around towers, measurement around towers, and of course, this enormous capability of computing, large eddy simulation, and direct numerical simulation, as well as the challenges which we have now with the weather forecast and climate models going to smaller and smaller scales and finer resolutions. And now I think about this is that parameterizations for this very stable boundary layer when turbulence is not the main driver is a big challenge, I would say. And there we really have to rely upon more field studies, not only considering turbulence, of course. If turbulence is not so strong, you have to be other processes take over. And that will be a big challenge for the future. And so that's put me into my last sentence with questions. Should we focus less on turbulence and have more appreciation for the other small-scale processes which are important in the atmosphere, like radiation, gravity wave drag, and all of that stuff? And Vincent knew about this already more than 100 years ago. Thank you very much.